All right, we're ready. Just a quick shout out to Nate Merrick for real nice hair today. You have anything to say?
Um, it's a really good problem.
Good one. Good one. Good thing you got good looking hair, cause. All right. So I'm going to use a highlighter, and we're going to try to pick out the important details of this problem here. The tricky thing with these problems is you have to write all of your inequalities yourself. Okay, so there's going to be a few that are obvious and then a few that are not so obvious, but let's have a read. Yum's Bakery bakes 2 breads, A and B. One batch uses 5 pounds of oats, so batch A uses 5 pounds of oats and 3 pounds of flour. Okay. Let's do that in a different color. 3 pounds of flour. And then let's see, batch B uses 2 pounds of oats. Oh, I wanted that in yellow. 2 pounds of oats and 3 pounds of flour. Okay. The company has 180 pounds of oats to use and 135 pounds of flour. So those are some constraints that we have, and we need to write some inequalities that will stay within those constraints. So when I see 180 pounds of oats possible to use, I'm thinking that there needs to be an inequality where some stuff is going to be less than or equal to 180. Right? And that would be like the oats equation, because they have 180 pounds of oats to work with. And they have 135 pounds of what? Flour. So then the amount of flour they use has to be less than or equal to 135 as well. So now we need to come up with equation or inequalities for, well, actually expressions for how many pounds of oats they use and how many pounds of flour they use based on the varying number of batches of which type of bread they make. So what are our variables going to be? We've been using x and y because we're graphing, right? So let's define our variables x and y. Let's let x be the number of batch A, the number of, what is it? I guess you just call it batch A. So number of batch A and number of batch B. So for every batch A, which would be x, so if you bake one batch of batch A, that's 1x, you use how many pounds of, what are we talking about, oats? So I guess oats would be the stuff in yellow. So let's write an oat restriction equation, or expression, excuse me. So 5x plus 2y has to be less than or equal to 180. So you use 5 pounds for every batch A plus 2 pounds for every batch B. And together, depending on how many different batches you make, that has to be less than or equal to 180. And same idea for flour here. So for flour, we use 3 pounds of flour for batch A and 3 pounds of flour for batch B. Is it the same? So 3x plus 3y has to be less than or equal 135. There are no other constraints that I see here except for 2 obvious ones. When we graph this, what quadrant are we going to be graphing it in? The first quadrant. Okay? So that means that we're not going to make any negative batches of bread. So x is going to be greater than or equal to 0, and so is y. So there is our system of inequalities, or our 4 constraints of our feasible, that will graph our feasible region. So let's go ahead and graph those here. So x is greater than 0 and y is greater than 0 are just going to be horizontal and vertical lines. So we are going to be to the right of this, meaning all of our x values are greater than 0, and above this, meaning all of our y values are greater than 0. So we're positive, positive quadrant. How to graph these two inequalities here, 5x plus 2y? What's the best way to graph this? Slope-intercept or intercepts form? Be easier to find the intercepts or rearrange it and write it in slope-intercept. Intercepts. So what would be the x-intercept if y is 0? So if I put 0 in for y and just forget about y, okay, what would x need to be when you multiply it by 5 to get 180? 36. So the x-intercept is 36, and the y-intercept would be then 90. So far we have to go up to 90 on our graph. So I'm thinking going by tens. Take a look at the other equation. What is 135 divided by 3? Well, 30 gets us to 90, right? So then how many more do we need? 45 more. So 1,505. Or I'm sorry, 45. 15 plus 30 is 45. So 45 there and 45 for the y. So there are your intercepts. So if we go by tens, we should be all right. So if each marking is 10, we'll be fine. So that's 20, 30, 40, 50, 60, 70. Okay. And I'll graph the red one in red, so that would be 45 and 45. And I'll do my best straight line here. That's not very good. Oh, I didn't graph it on the x-axis, did I? Undo that. It's right here. And we are talking about being on the 0, 0 side of that line. So we are down here. So now we have essentially a triangle. The blue line is going to go to 36, which would be right about there, and to 90 on the y, which is all the way up here. Ooh, that looks really close to the point 30, 20. Wonder if it is. So your feasible region now, all the possible points you have are right in here. Any point in there would satisfy all of your constraints. We're interested in what specific points? What specific points are we interested in? The vertices. So we want to know what that is, and that. So you need to find all the vertices of the feasible region, because eventually that's what's going to maximize our equation for profit. So on the next page, Yum's Bakery wants to maximize its profits. One batch of A yields a profit of $40. Oh, that's a lot of money. Crayon. So we'll take $40 for a batch of A, and a batch of B is $30. So what would our profit equation look like? Well, let's say P is profit. And so then P is going to equal $40 times every batch of A we make, which is our X, and $30 times all the batches of B we make, which is our Y. And so we take this profit equation and we are going to substitute every vertice of the feasible region that is going to maximize this, because we want a maximum profit, so we want to maximize. Well, if we flip back to the previous page and look at our vertices, 3 of the vertices are easy to find and 1 of them is not so easy. So if we take a look at our vertices, down here we have 0, 0. Is that going to give us a maximum profit if we don't make anything? No. Right here, this vertice is 36, 0. So we need to test that. This right here is 0, 45. And then what is this one right here? I'm not sure. It looks like it's at 30, 20. But I'm not 100% sure. So how am I going to find that? How do I find the intersection of 2 lines if I know the lines? Take the 2 lines and put them in a system of equations. So I need to take this line right here, the 5x plus 2y equals 180 line, and set it equal to the red line. So let's do that. So what we finally need to do here is solve this to make sure that we know what that intersection point is, because we can't just be sure looking at the graph that it was what we thought it was. So I'm going to solve this and I'm going to eliminate y. So I'll multiply the top equation by -3, and so then I'll have here -540 and the bottom equation I'll multiply that by +2. And I'll go ahead, I'll eliminate y's, so I'll be left with -9x is equal to -270. And so x then is equal to 30, which is that kind of what we thought it was? That's what it looked like on the graph. So if x is 30, plug that in for either one here, put it right in there, we would have then 90 plus 3y is equal to 135. So when does 3y equal 45? When y is 15. So that was the point 15 or 3015, not what I thought it was. So my graph wasn't perfect. So this point back here then we just determined was 3015. So we need to test those, essentially these 3 points in our maximize equation. That one, and that one. We don't really need to worry about 0, 0. And I'm thinking 36, 0 isn't a real winner either. So those points were 36, 0, 0, 45, and 30, 15. So when you substitute those values in for x and y, one of them is going to give you the maximum profit. So we'll run those numbers and determine which one works. So wrapping this up, we're finishing this up. The maximum profit we found to be 1,650 when you bake 30 batches of loaf A and 15 of batch B. So there you have it.